We now turn our attention to the electrical properties of dendrites. Traditionally, it was believed that few, if any, voltage-gated ion channels were expressed on dendrites. This meant that action potentials couldn't be generated in dendrites, and that when a synaptic potential was generated at the distal end of a dendrite, of course, this potential had to be conducted to the soma, and the only way it could be conducted was by passive conduction, electrotonic conduction, which meant that the synaptic potential when it arrived at the soma would be much smaller. And indeed, the size of the potential when it finally arrived at the soma was determined by the time constant and the length constant of the membrane. Research over the past 20 years or so has shown, in fact, that our initial assumption that there were no voltage-gated channels in dendrites was incorrect. Indeed, we now know that voltage-gated sodium channels and potassium channels, as well as calcium channels, are expressed in dendrites, and this leads to the generation of sodium and calcium spikes in the dendrites of many neurons. And one of the consequences of this is that synaptic potentials can be amplified by these voltage-gated channels. We will be discussing two examples of voltage-gated channels being expressed on neurons. And the first example comes from work from Stewart and Sachman, published in Nature in 1994. And in this work, they recorded using brain slice preparations. They recorded from pyramidal neurons in the neocortex. They first patched onto the dendritic membrane using patch clamp electrodes. They pulled patches of membrane from the dendrite to achieve outside-out patches, and then voltage clamped these patches to record any currents generated by voltage-gated channels. And indeed, what they found is that when they depolarized these patches of membrane, these taken from the dendrite, they recorded very rapid inward currents that look like they should be generated by voltage-gated sodium channels. And indeed, when they applied TTX to the bath solution, and recall these are outside-out patches, so the TTX should block the sodium channels, they found that this rapid inward current was completely eliminated. And in fact, this effect of TTX could be partially reversed by washing out the TTX. So the conclusion of these experiments is that voltage-gated sodium channels indeed are expressed and are found on the membrane of dendrites of pyramidal neurons in the cortex. Stewart and Sachman then did a very elegant experiment to determine whether these voltage-gated sodium channels could lead to propagation of action potentials in dendrites. What they did was to patch onto a pyramidal neuron, again this is in a brain slice, with two different patch electrodes, and both of these electrodes were in the whole cell recording mode, so they were recording the intracellular voltage both from the soma of the pyramidal neuron and from the dendrite of the neuron. In this particular example, in the upper left, when a depolarizing current was applied to the soma electrode, this depolarized the soma and led to the generation of an action potential in the soma, and then at a slightly delayed time they recorded a smaller action potential that appeared in the distal dendrite. The same type of recording was obtained if they depolarized not the soma but the distal dendrite. So here they're applying a depolarizing current pulse to the distal dendrite and recording voltage both in the dendrite and in the soma. And again, they find that there's initially a large action potential in the soma and then a smaller potential, slightly delayed, in the dendrite. The same type of response is seen if they used a more physiological stimulus. In this case, they are stimulating the afferent fibers that synapse onto the pyramidal neuron. So they have one electrode stimulating these afferents, and then the two electrodes recording the voltage from the dendrite and from the soma. And once again, we see a soma spike followed by a dendritic spike. Well, I've been assuming that the response recorded in the dendrite is indeed an action potential, but it's also possible that this response was not actively propagated through the dendrite, but rather was just a passive electrotonic response seen following the action potential in the soma. So it's quite possible that an action potential was generated in the soma, perhaps initiated at the axon hillock, and then just passively conducted back through the dendrite to the distal dendrite and to the patch electrode that's recording the response. So these records don't guarantee that this response in the dendrite is a sign of a active propagation of an action potential through the dendrite. Well, they did another experiment that supports the hypothesis that this, in fact, is active propagation of an action potential in the dendrite. And what they did was to measure the delay between the peak of the response in the soma and in the dendrite and plot that as a function of distance along the dendrite that they're recording. And what they find is that the further out, away from the soma, they record the response, the longer is the latency of the response. And this suggests that there is a delay that could be generated by active propagation along the dendrite, and the farther along you are, the longer it takes to for the action potential to reach the distal end of the dendrite. However, this is not a guarantee that we are seeing active propagation, because as we know, even electrotonic propagation shows a delay due to the membrane capacitance of the dendrite, which would lead to perhaps similar behavior of a greater delay as you move down the distal dendrite. Stewart and Sockman did one additional experiment to test their hypothesis that the responses they were recording in the dendrite were in fact action potentials that were actively propagated from the soma back into the dendrite by back propagation. And what they did was the following. They put a sodium channel blocker, QX314, in the patch electrode that was recording the response from the dendrite. Now, unlike TTX, which works by blocking the sodium channel pore from the outside, QX314 works by blocking the channel from the inside. So they are introducing the sodium channel blocker into the cytoplasm through the patch electrode, and this should block sodium channels. So what they obtained is the plot shown in the bottom of this slide, where they're recording the response from the patch electrode in the soma, and also the response recorded from the patch electrode in the dendrite. And initially, they have broken through in the soma, so they're recording the soma response, but they have patched onto the dendrite with the other electrode, but they don't actually break through until the break-in arrow is shown at about 40 seconds. And then they can record the voltage from the dendrite from that point on. Well, you can see the responses they record. I'd like you to explain why they obtain these responses and what these responses tell us about whether the spike they recorded in the dendrite is indeed a sign of active propagation from the soma to the dendrite. So think about this, and we'll be discussing this figure and what it means in class.